Hi, Honors Chem. Just want to go over a couple of different problems we're going to see in kinetics. This one is writing rate laws from experimental data. So you'll have initial rates, and this will correlate to your experiment where we did the same thing 6 or 7 times. So in this example, we have 4 different trials. We're doing the same experiment. It's a gaseous reaction of nitrogen monoxide with diatomic oxygen to produce nitrogen dioxide. The same problem is in your textbook on page 617, and the same concept is in the PowerPoints on slides 18 and 19 with a different example. So we're trying to find a rate law to represent the kinetics in the reaction. We're looking at the effect of concentration on rate. So we're going to set up our rate law. Rate equals K, and then check the dependence of the rate on each of our reactants. So we need to find a couple trials where we see a change in concentration and a change in rate. If the rate doubles and the concentration doubles, that will tell us it's first order. If the rate quadruples when the concentration doubles, that will tell us it's second order. And if there are any higher multiples there, if we double the concentration and the rate is 8 times more, that's going to be third order. If there's no effect, it is 0 order. Okay, so we're going to start off looking at trials 1 and 2. In 1 and 2, the nitrogen monoxide is held constant, oxygen doubles. So because the rate of oxygen doubles, and the rate doubles, that tells us that the reaction is first order with respect to the oxygen. We see the same effect here. It doubles again, and the rate doubles again. Notice in all of these, the nitrogen monoxide stays the same. So you can compare these 2 columns without looking at the effect of the nitrogen monoxide. Okay, so we can adjust our rate law. In terms of the oxygen, it is first order. Next, we want to look at the effect of the nitrogen monoxide. So the trials we have to choose here are 2 and 4, because in that one, the oxygen is held constant. From 2 to 4, our nitrogen monoxide doubles. It's a factor of 2. Our rate increases by a factor of 4. Okay. So because this is a factor of 4, that tells us it is doubly dependent on the concentration of nitrogen monoxide. So our rate law will include our nitrogen monoxide, but it is second order. It varies as a function of the concentration, doubly dependent, squared. Now that's our rate law. We can also solve for the rate constant K. Okay, so that's the first step, finding the rate law. We can choose any one of these trials and just substitute in for rate, concentration of oxygen, and concentration of nitrogen monoxide. Pick any one of those and solve for K. A little bit of algebra tells you that K is equal to 7,100. 7,100, so do the sig figs. The units of K become a little confusing. So this reaction is first order in oxygen, second order in nitrogen monoxide, third order overall. So if we look at our units, rate has units of molarity per second. To compare that to the other side of our equation, oxygen and nitrogen monoxide are in concentration units, so that's molarity as well. And this one is squared. So to make both sides of our equation equal, our K must have units of 1 over seconds, we have to get two of these to cancel, times molarity squared. The units on K will change depending on reaction order. So this is your value for K. This is your rate law. We can substitute that K in there for any situation we have. And that's rate laws from initial concentration in experimental data.